Figure given below shows a circular coil of n turns and radius a connected to a battery of EMF E through a rheostat. The rheostat has a total length L and a resistance capital R. The resistance of the coil is small r. A small circular loop of radius a dash and resistance r dash is placed coaxially with the coil. The center of the loop is at a distance x from the center of the coil. In the beginning, the sliding contact of the rheostat is at the left end and then it moves towards the right at a constant speed v. Find the EMF induced in the small circular loop at the instant the contact begins to slide, and in the B part it has slid through the half the length of the rheostat. So if we consider this problem, we consider in this way. I am drawing it in an enlarged way. So over here we are having a circular loop like this, which will be carrying a certain current, and the current will be a function of time. It is because of the fact that the rheostat's resistance is continuously changing. So as a result of this current carrying coil, which is having n turns and radius equal to a magnetic field will be produced at a distance x. A magnetic field will be produced at a distance x, which is the center of this smaller coil which we have. So this smaller coil is having a radius a dash. So the magnetic field at a distance x can be written in this way: B is equal to mu naught Ni a square upon twice of x square plus a square to the power 3 by 2. So this is the value of magnetic field due to this current carrying circular coil at a distance x, and hence the flux through the small coil can be written as mu naught Ni a square upon twice of x square plus a square to the power 3 by 2 times of pi a dash square. So we have multiplied it with this area, and over here we can calculate that the rate of change of flux is regarded as the magnitude of EMF. So if we calculate from here the magnitude of EMF, which is equal to d phi by dt, so we can write it in this way: mu naught n pi a square into a dash square upon twice of x square plus a square to the power 3 by 2 times of di by dt. So we wish to calculate this rate of change of current over here now. So apart from this parameter, we are left with the finding of this value of the rate of change of current. So we are considering it in this way, that the x length of the rheostat will offer a resistance which will be equal to Rx upon L. The L length of the rheostat is offering a resistance equal to R. So the X length of the rheostat will offer this resistance, and hence the current through the battery can be written as I is equal to E upon the resistance offered by this X length, that is Rx upon L, and the resistance of the coil, which is equal to small r. So from here, if we calculate the value of di by dt, so di by dt can be written in this way, that we can take El as constant, and we can differentiate this part Rx plus Rl with respect to time dt. So if we solve this expression, we get di by dt is equal to El, and if we differentiate this expression, we can differentiate it in this way: Rx plus XL whole square, and we will get a minus of derivative of this entire function, that is derivative of Rx plus Rl with respect to dt. So from here we obtain a value equal to El, this will be R, and dx by dt can be written as V. So the term dx by dt is written as V, and the derivative of RL with respect to dt will become 0, because it is constant, and we are left with this expression Rx plus XL whole square with a negative sign. So since we are writing di by dt magnitude, so we are omitting the negative sign for the time being. So this is the value of di by dt which we have. So if we put this expression in the value which we have calculated previously, that is this expression of EMF induced, so we will get the value of EMF induced as a function of x. So if we do so, we obtain the EMF induced value as, so EMF induced can be written as mu naught n pi a square a dash square upon twice of x square plus a square to the power 3 by 2 times of ERLV upon Rx plus RL whole square. Now the question is asking us to calculate the value over here at 2 instant when the contact began to slide and when it has slid through this half the distance or half the length of the rheostat. So over here we can do a simple thing. Now for the A part, the value will be when x is equal to L. So if we put x is equal to L over here in this expression, we will obtain the value of EMF induced in the A part, which we are calling it as EA. So it will become mu naught n pi a square a dash square ERLV upon twice of x square plus a square to the power 3 by 2. And if we put L over here, we can take L square common, r plus r whole square, and we can remove this L from here. So on cancellation we obtain this value that the EMF induced in this part is equal to mu naught n pi a square a dash square ERV upon twice of x square plus a square to the power 3 by 2 into L times of r plus r whole square. So similarly in the B part, what we have to do is we have to put x is equal to L by 2. So if we put x equal to L by 2 in the above expression, we can obtain the answer easily. So I am leaving it that part for you. So this is how we solve the value of EMF induced for this particular problem.